Okay, so let's look at this assumption number 2 called identification. So I have this kind of strange looking equation up at the top, but all that means is that we're ruling out a case where all of our observations on x are on a particular value x naught. Okay? And the reason we rule out this case is because this doesn't give us any variation in x that we need to identify the mean of y as a function of x. Okay? If we're trying to fit sort of a regression line, we just have a bunch of observations on a particular point, and we can't do it. Okay? The third assumption is that the error has a 0 mean. Well, so basically what we rule out, so here I've drawn a picture of an error having a positive mean, okay? And we just rule this out because we don't have any information that would help us separately, sort out whether our error just had a 0 mean and the regression line was shifted up, or whether the error had a positive mean and our regression line was shifted down. Okay, we don't have any information to sort of separately to sort those two possibilities out. So we just assume that the error has 0 variant or 0 expectation. Okay. And I should say, another way to say this is that those two, the expectation of the error and the intercept of the regression line are not separately identified. That's another sort of piece of terminology. That just means we don't have any way to sort them out with the data. Okay, our fourth assumption is homoscedasticity. So what is homoscedasticity? It just means that we're going to assume that the variance for all of our errors, the variance is equal to sigma squared. Okay, for all, that's supposed to be all little I, but my autocorrect made it capital I think. Okay, so this is a picture of what the opposite of homoscedasticity might look like. This is called heteroscedasticity. And here I've drawn it so that it looks like the error variance for low values of x is much higher than the error variance for higher values of x. Okay? And so we're going to rule that out for now. That's actually not a fatal problem. We can deal with it, but at least for now, we're going to assume that we have homoscedasticity and not heteroscedasticity. Okay, so right about now, you're probably thinking, what is the etymology of homo and heteroscedasticity, and is she even spelling it right? Because, in fact, my autocorrect kept trying to replace K with C whenever I was typing homoscedasticity. Turns out that the autocorrect in PowerPoint has not read this article in Econometrica on the etymology and the correct spelling of homoscedasticity and heteroscedasticity. So anyhow, I've put this up on the website. You can peruse this at your leisure. But this will answer all your questions about the origin of these words. Okay, and then the fifth assumption is that we have no serial correlation. So that means, in other words, that the sort of errors are not correlated if they're coming from if they're associated with different observations. Okay? So a stronger way of saying this is that the errors are independent across observations. We don't need to impose that. We're just going to say that they're uncorrelated. Okay? Here's a picture. I drew a picture of what positive serial correlation might look like. So here we have, here we have sort of some positive errors over on the left side, and then if you have one positive error, the close by errors are also likely to be positive. So you have sort of an area where errors are mostly positive, and then you get sort of a negative error, and then sort of most of the errors close by are likely to be negative. So this is what positive serial correlation might look like. The errors are kind of clumped spatially like this. Okay? Again, this is not fatal. We can deal with this, but we're going to assume for now that we don't have it. Okay, and then as I said, assumptions 3 through 5 could be subsumed under a stronger assumption that epsilon I are IID normal 0 sigma squared. Okay? So we don't typically need this assumption. Sometimes we impose it. That just means that, you know, conditional, yeah, basically the error just has a little normal distribution that looks like that.